Okay, I think we can slowly start this session. Welcome everyone and good morning to this concurrent session of the IAEE conference on wind. I am your chairman for this morning's session. My name is Efthymios Karangelos and I am a postdoctoral researcher representing the University of Liège. Before giving the word to the first speaker, I should say that today we have three very interesting papers and we will see about 25 minutes of presentation for each one of the papers, and then followed by 5 minutes of question and answer. If you do wish to ask a question, please try to use the chat or to raise your hand to let me know of this, and then I will give you the floor, and then you could, let's say, unmute yourself or open your camera to ask the question. So with this, it's now time to introduce the first paper that will be presented by Dr. Javier López Prol, who is a postdoctoral researcher in the Wegener Center for Climate and Global Change in the University of Graz in Austria. He holds a Master in International and Development Economics from the Complutense University of Madrid in Spain, and a PhD in Economics from the University of Graz with graduate status at UC Berkeley. His research addresses the regulation, profitability, and diffusion of variable renewables, as well as their effects on wholesale electricity markets. Please, Javier, the floor is yours.
Thank you very much. I will share my screen. So since we applied for this 2 years ago already, due to COVID, I moved to Yonsei University. So good afternoon from South Korea, good morning for everyone in Europe. And indeed, I will be presenting about the benefits of spatial integration and deployment coordination of wind power to achieve a stable, a firm generation pattern. And this is work in collaboration with Iain Staffell, Stefan Pfenninger, Fernando de Llano, and Anxo, Calvo, Silvosa. So you all know by now that variable renewables, wind and solar, are the cheapest electricity generation technologies in terms of levelized cost. This is a figure by the International Renewable Energy Agency, where we can see that levelized costs, that is the unit cost of electricity for solar and for wind, are already within or even below the range of fossil fuels on average. In many locations, they are even lower. Indeed, the last landmark report from the International Energy Agency to achieve net zero emissions by 2050 highlights wind and solar as the main mechanisms to decarbonize electricity generation. You can see that from a negligible share nowadays of wind and solar, less than 10%, both combined, we will go towards about 70% share of wind and solar generation in 2050. And wind will be the main electricity generation technology by then. The problem of variable renewables is indeed their variability. They are not dispatchable, so they cannot be switched on and off as we want, but they generate according to weather patterns. You can see here the wind generation pattern in Germany for some months between November 2018 and the first months of 2019. And the hourly generation profile, you can see that at some points it has power above 40 gigawatts, but it has also other moments with almost zero generation, very close to zero. And in these lows, these extreme lows, generate most of the integration costs for the electricity system. They are expensive. So integration costs are the additional costs caused by variable renewables to the electricity system to tackle the intermittency of variable renewables. Here you can see an illustration of the costs of wind. The levelized cost at this moment, this is from 2013, so it's already below this level, was about 60 euros per megawatt hour. The dashed line represents the levelized cost, which actually declines as penetration increases, thanks to learning by doing, etc. But even assuming it's a constant levelized cost, we can see that integration costs are negligible at low penetrations, even negative at the very beginning, but they increase, represented by the solid black line, as penetration increases. And integration cost comprises many different things. Here they are divided into grid costs, balancing costs, and profile costs. To illustrate this, just mention that most of the costs are profile costs, and they derive from the variable generation pattern of wind. And that entails that we need more flexibility in the system, both from the supply side as dispatchable peaking generation technologies, such as peaking gas, for instance, but they are more expensive. And we will also need flexibility from the demand side, meaning demand response from consumers. And that's expensive. First, because peaking technologies have to be idle for most of the time. So it's high cost capacity that only generates when wind is not generating. And demand flexibility has still to be implemented because it's very low nowadays. So it will need both behavioral changes and further technological development. At some point, integration costs will become even higher than levelized costs themselves. So the figure I show you about levelized costs is very interesting, but it doesn't tell us the full picture. Integration costs are equivalent to the cannibalization effect, which means that variable renewals market values decline as their penetration goes up in wholesale electricity markets. We have estimated that for California, and we are doing it also for Europe nowadays. It means that curtailment will increase in the future, so it's electricity that can be produced by variable renewables, but it won't be produced because there is oversupply at peak times. And also we are working on something relating curtailment that I will be presenting as well in the IAEE in case you are around there. And there are so many other types of integration costs. Another example could be startup costs of conventional generators. So they have to start up more frequently to adjust their generation to the intermittency of variable renewables, and that has high costs for those generators. So basically, the problem is that variability of wind and also solar increase the system cost of those technologies and therefore make their further penetration more difficult and more costly. So what we try to do here is to optimize the capacity factor volatility trade-off. So we define firm wind as the capacity of wind power to provide both reliable and certain generation pattern. A reliable generation pattern means that the capacity factor of wind, capacity factor is just generation, actual generation divided by potential generation, what the capacity could produce at given full resources. So reliability means that the capacity factor, a minimum capacity factor, is provided all the time or most of the time. We can set any arbitrary value. For instance, 99% of the time. We are 99% sure that we will have a minimum capacity factor for the whole time, basically. That's reliability. Uncertainty means that most of the generation, most of the capacity factor during the year is concentrated around a few values, around the mean. So we know more or less how much we will be generating. So that again reduces integration costs because it reduces the need for flexibility. So what we have nowadays is an unreliable and uncertain pattern because we have many hours with close to zero generation. This is the capacity factor down here. And we also have a very spread out distribution of the capacity factor, with hours with low generation, hours with middle generation, and hours sometimes with very high capacity factor, such as the peaks that I showed you before for Germany, with hours even above 40 gigawatts. We could also have a more certain pattern, more concentrated around the mean, but still unreliable because we have many hours around zero. And we would have the opposite, a reliable generation pattern where we don't have any hours close to zero capacity factor, but it's still very spread. So there is uncertainty about how much generation we will have on each moment. And the goal is to achieve both certain and reliable generation pattern. So reliable in the sense that we never have zero capacity factor. We minimize the probability of low wind events, which are the most costly. And we also have a certain generation pattern in the sense that most of the times we generate at a certain range within the mean. For instance, we define it as the mean plus minus 50%, just for illustrative purposes. So what do we do? We apply modern portfolio theory, which is a framework coming from finance, to optimize, as I mentioned before, the trade-off between high capacity factors and low volatility. Low volatility measured as standard deviation. First of all, the data we use is hourly. We have 111 regions comprising European states, European countries, US states, and Chinese provinces for 30 years. So that's about 30 million observations. You can see here the kind of data that we have. We have the different countries in Europe, these gray dots, according to their mean capacity factors during these 30 years and their standard deviation, the standard deviation of the capacity factor. The results I will be showing you, by the way, it's not yet with the full sample, but just with a smaller subsample of 10 years. So these are not final results yet. So you can see here, for instance, countries with low capacity factor, and up here, countries with high capacity factor, for instance, Denmark, Great Britain, Sweden, etc. What we want to see is how integrating those countries and optimally deploying installed capacities across countries can improve this trade-off between capacity factor and volatility. As an easy example, we can see the case of Mibel. Mibel is just the Iberian electricity market, which comprises only two countries, Spain and Portugal. So we build efficient frontiers, which are these colored lines, which are the combination of portfolios that give us the minimum volatility for each level of capacity factor. So each point along the line, it's a portfolio. And a portfolio is the relative shares of wind installed capacity per country. For instance, in the case of Mibel, we only have two countries. So for instance, this portfolio would be only Spain, 100% of installed capacity in Spain. In the middle would be 50-50, 50% capacity in Spain, 50% in Portugal, and so on. So each of the points along the frontier is a different portfolio of shares installed capacities across countries. So through this mean variance optimization framework by Harry Markowitz, who was the one who invented this kind of framework to optimize financial portfolios in stock markets. So we calculate the efficient frontier first for each of the configurations. Each configuration is a current power region. For instance, Mibel, as I said, is the Iberian electricity market, Apex Spot is the Central European electricity market, and Nord Pool is the North European electricity market. And here we have Europe comprising all these countries that you can see here. We did this for Europe but also for China and for the USA, with the different individual countries and provinces in gray and the different configurations. On each of the frontiers, we highlight one point, which is the technical optimum, is the point at which we maximize capacity factor per unit of volatility. So this is the portfolio that gives us the optimum generation pattern. As we move up along the frontier, we go towards higher capacity factors, but also higher volatility. And as we move down, we go towards lower volatility. So it depends what we prioritize. As a hypothetical exercise, we combine all regions that we have and we make an intercontinental configuration. So what we can see is that the higher the spatial integration and deployment coordination, the better we can optimize this trade-off. So the upper this efficient frontier and the more to the left, the better, because that means that we can have higher capacity factors at lower volatilities. As I mentioned, the extremes would be the portfolios with maximum capacity factor in the upper right corner and the minimum volatility in the lower left corner. The case of the maximum capacity factor is just the 100% of capacity installed in the region with the highest average capacity factor, which in our dataset is Nebraska in the US. The result we get at the end is the shares of installed capacity per country, state, and province. This is just illustrative, but as I said, it's not final results yet. But the point is that by doing this, we are able to minimize first the cumulative probability of low-in events. So for instance, we can see that the probability of a capacity factor below 20% for Europe, even for the optimal European portfolio, is above 25%, but in the intercontinental configuration would be less than 10% probability of capacity factors below 20%. And this brings benefits even for the regions with the highest capacity factor, because as you can see here, this is the cumulative probability of capacity factors in Nebraska, in the region with the highest capacity factor. And you can see that it still has high probability of capacity factors below 10%, around 10%. But with even the USA configuration alone, that probability is almost zero. So there would be no hours of capacity factors below 10%. That's great, because that's what causes most of integration costs. So basically, from initial cumulative probability for each individual country, what spatial integration and deployment coordination achieves is to increase reliability by moving it to the right. So we have less probability of low-in events here, and also increasing the slope of this cumulative probability function, which means that we have more certainty, because most of generation is within this range. So in conclusion, by integrating countries and optimally allocating capacities across countries, we can achieve higher reliability to the right, here measured as the lowest capacity factor. In this case, we establish the range as the mean plus minus 50%. You can see that countries in autarky, individual countries, have low certainty and low reliability up here, but as they become integrated in subcontinental electricity markets or continental electricity markets, or even intercontinental electricity markets, both reliability and certainty increase. in the optimal portfolio of the intercontinental configuration, we would reach 99% of the hours with capacity factors above 17% and within the mean plus minus 50%. So that's a very reliable and certain generation pattern. So I would like to conclude with the limitations that are all that you can imagine and more. This framework, first, it comes from finance, so it's kind of a new thing. I mean, it has been applied to energy before, but it has some limitations. The first one is this is a technical optimal. So we would need to also talk about the costs of capacity and the cost of volatility. So depending on relative costs, we would go towards higher capacity factors or towards lower volatility along the frontier. So we would need to monetize these estimates. The second, of course, is political and even technical feasibility of integrating such markets. At the end, we come up with a very ambitious, let's say, configuration, but these configurations are actually very feasible. Some of them are already working nowadays. These configurations are based on actual power markets today, and integration and deployment coordination in these regions is more feasible. We would also have to balance the cost of interconnection, the cost of integrating countries, with the cost of alternatives. Perhaps with decreasing costs of storage, storing is just easier than interconnecting. Although interconnecting has other co-benefits, such as also balancing not only supply, but also demand, different demand patterns across countries. And finally, spatial resolution, we do it at a country level, but it could be done much more detailed in sub-national or sub-state resolution. That's possible with the Renewables Ninja database that I mentioned. So I would like to hear more from you, what other limitations you can think, and if you have any questions, I'm very happy to also discuss them. Thank you very much.
Thank you, Javier, for this very nice presentation and also for keeping the time. So at this time, I would like to ask the audience if there are any questions. You can either let me know in the chat that you want to ask a question, or please raise your hand or whatever, and then I will, of course, give you the word. Let's just wait a minute for this, see if there is any question.
These are the configurations, just in case you are curious about how they are built.
Maybe while we wait for the audience to, let's say, let us know if you have any questions, I can start by asking you a first question, just to warm up. What I wanted to understand is what's in your data. So typically the capacity factor is, as you showed in your slide, the power output divided by the maximum capacity of the resource. Now, depending on where you source data, this could be either the purely what is the wind potential, so how strong is the wind in the locations that you are linking.
Yes, exactly.
So this is what is in your model. So it's just the resource potential.
Yes, the original data comes from, as I mentioned, Renewables Ninja. And what they do is to reanalyze wind potentials according to both current installed capacities and technology options today to derive capacity factors, hourly capacity factors, even in regions where there is low generation nowadays. So they come up with hourly patterns of capacity factor for the last 30 years. Here, for instance, you can see the summary statistics. So this is the mean capacity factor per country, per province, country, and state, and the coefficient of variation. So this is input data, just time series of hourly capacity factors for the last 30 years for each region.
Okay, Then in that case, what I wanted to discuss with you is the fact that, okay, I understand the motivation for trying to maximize the capacity factor divided by the standard deviation. Let's say to have, as you shown very nice, a certain profile. But I am a little bit curious about this, the gravity of these so-called low wind events, because depending on when they happen, for example, if these happen in periods of low demand, then they are not as critical as we think. And this is not
Yes,
represented
indeed.
in your model, as far as I understand.
Yes, and that's a critical question because it depends how much they cost on how much this framework is useful or not. Because, for instance, as you said, if the value of electricity here is low because there is no consumption, then this is not a huge problem. And this depends a lot on different countries, on the demand profiles that countries have. When this happens, is quite random. So I would say that it causes cost not only because it doesn't match the demand profile, but also because it's very random. So anyway, there has to be backup capacity behind to back up those moments of very low wind generation. So regardless of when they happen, the problem is that they cause high cost because we need to have backup capacity behind. But indeed, it would be nice to have a quantification of how much are exactly the costs that those low wind generation events cost.
Yeah, do you see a way of expanding your study to, let's say now you're looking into the probability of low wind events, but also to somehow take into account the statistics of the demand here? So to find out, let's say, the probability of low wind events when we at the same time we have demand, or
So one option would be to translate capacity factors into the value of electricity at each point, which would be merging somehow this framework with the cannibalization effect that I mentioned before. So instead of having here a capacity factor, we could have the value of electricity at each moment. That could be one way to integrate demand as the value of electricity at each time. The problem is that that's likely to change as penetration increases, because the cannibalization effect, what it means is exactly that as more variable renewals generate at the same time, then their value declines over time. So that would be more, let's say, unstable results because they would change over time. And they would change according to changes in in demand patterns as well. But there could be integrate that. Yes.
Now you spoke of this cannibalization effect, and I wonder how we will see this in the analysis of the capacity factor, because the capacity factor is, let's say, divided by the capacity by default, so you don't see larger capacity when you look at the capacity factors.
Yes, so capacity factors tell us just how much electricity is generated, divided by potential, divided by the potential, but integrating the cannibalization effect would entail not only how much, but how valuable that generation is. For instance, if we have high generation at night for the model, that would be great, but if we integrate the cannibalization effect, we would see that during night, the value of electricity is lower. So actually, we would be favoring generation patterns that generate more during peak times.
Yeah, I understand. Okay, let us try to see if there is again, please, in the audience, if you have some question, now would be a good time to ask before we move on to the next presentation. I don't think I have missed some reaction, but if there is somebody who really wants to ask a question, please feel free to also unmute yourself.
Yeah, maybe I have a question.
Yes, please.
Have you solved any way to account for transportation cost being a limitation to that spatial aggregation of different markets? I don't really have a ready-made solution for you, but like when you said the whole Europe is working better than isolated country, but there is interconnection cost, like try to estimate how much interconnection would be needed or something like that.
We didn't account for for integration costs, what we did was, let me see if I have it here, was to make scenarios, let's say, with constraints. So what if the maximum interconnection is 15%, for instance, which is the long-term goal of the European Commission, to have 15% interconnection across all countries. So instead of doing it with costs, which would be a bit more complex, we just set constraints, and then by these constraints, we have worse frontiers, worse efficient frontiers, because then installed capacities have to be shared differently. So we have worse frontiers the more constraints we set. But we could set constraints to have different interconnection capacities across countries. That could be one way to implement somehow the cost of integration or the limits of integration across countries.
Okay, thank you.
Maybe I can follow up a little bit on this as well, since we have a few minutes spare. So in practice, we will indeed have some limits of interconnection that are defined not only by the capacity between the countries, but also by security and so on. Which means that it would be, let's say, too optimistic to assume that we can arrive in Europe at a situation where we have the same capacity factor across Europe, right?
Mm-hmm.
Now,
yes.
My question is if you think that there could be a situation where for one country, let's say a country with very strong resource potential, it is not beneficial to share this with the other countries through interconnection. So the autarky situation, given the constraints of interconnections, gives a better solution for one country with respect to, let's say, the shared solution. And if so, how could we solve this type of problem?
So you mean when autarky could be preferential from integrating?
Yeah.
According to this framework, I can't think of any example in which autarky would be better under this framework. But of course, there could be political economic reasons. For instance, a country with a high capacity factor would mean that they probably had lower electricity costs. But if they integrate with other countries, they will have higher electricity costs. So that's the case now in Norway, for instance. They have very good resources, so they have low electricity costs. If they integrate with the rest of Europe, basically the suppliers will benefit from it because electricity costs will go up. So there will be producer surplus, but the consumer surplus will be reduced because electricity costs will go up.
Yeah.
So yes, there is political economic questions about the distribution of producer and consumer surplus.
Yeah. Okay.
Right,
Okay, I think we can now thank our first speaker for this very nice presentation and
thank you very much.
Taking care of all these questions, and progressively move on to our second paper for today that will be presented by Xinyu Li, who is a researcher in economics at the University of Pfenninger. He specializes in the field of industry organization, behavioral and experimental economics, energy economics, and competition policy. He has published several papers on the topic of information disclosure in the business practices. Recently, he is interested in renewable energy and has conducted 2 projects on it. One is about the trade-off that wind turbine operators face between signing a long-term maintenance contract with the OEMs and signing a short-term contract. The other is about how to design a simple, transparent, and efficient policy to promote wind energy. I think this is more closer to the topic of the paper, which is a study of the price guarantees and subsidies in wind farm auctions. So, Xinyu, please, the floor is yours. We can have 25 minutes of presentation and then some discussion.
Okay, good morning, everyone. And I will present a topic about wind farm auction design. So it's an experimental paper, and it's a joint project with Marco Haan, Onderstal, and Jasper Veldman. And 3 of us from University Groningen and Sander from Amsterdam University. Okay, so I guess like the background is clear for most of the people who are interested in renewable energy. So wind power is a very important tool to help the energy transition to the low CO2 emission energy system. And many countries promote wind power a lot. And many countries open different locations for onshore, offshore wind farm. And to allocate the wind farm resource to different producers. And most governments use auction to allocate the license for production. And obviously, to design this allocation system, you need some kind of policy which is efficient, transparent, and in the other way can like generate more revenue for the government. And we already noticed the change in this wind farm industry, because at the beginning we all know like wind farm doesn't earn enough profit to cover the cost. So in that sense, like government need subsidize the wind farm production. But recently, due to the cost reduction of the wind farm, and also due to the electricity price probably a bit higher and so on. So there's many factors makes the wind farm profit increase a lot, so that they don't need the government subsidy. They can still build and operate the wind farm and supply electricity to the market. And in this kind of background, the government is considering how to allocate the wind farm license, given there's no subsidy needed, and investors can like earn positive profit. So this is basically the background of our study. Like in this scenario, how do we allocate the wind farm license, and what's the best way to do so? And in fact, in reality, and many countries use auctions to allocate wind license. And for example, in the USA, and they use like a cash auction, this ascending clock. So basically say, okay, many bidders just participate in this auction, and then there's a clock, and then everyone just submit how much they want to pay for this license of the wind farm. And until the last moment, like say, okay, you are the highest bidder, and then you win this. And the feature of this auction is like it's a multi-round. It's not like a one-round auction. So basically, everyone have many different rounds to beat their willingness to pay for this license. And also you receive feedback because you observe like how much other people bid for the first round, and then you can adjust like increase how much you want to bid for the second round, and so on, so on, until the last round no one competes with you, and then you are the winner. And in this like kind of auction, please notice like there's no any subsidy from the government to the wind farm builder. Basically, wind farm estimate they will earn enough profit to cover the cost, so they don't need any subsidy. And similarly happening in the UK. And in the UK, in the past, like they need subsidy, and the government use contract for difference auction. So basically promise the stable electricity price the builder will earn in the future. And then this kind of like mechanism to subsidize the builder. But recently, from last year and this year, they start auction without compensation for that. So basically they call it a royalty plus cash auction. So basically it means that, okay, right now, if you want to build a wind farm and get the license, and first you have to pay a upfront payment, basically it's a one-time transfer to get the license. And in future, and the government will share like a certain share of the revenue of the wind farm cash flow. So basically you can think that, okay, the government will take a part of the future revenue from the wind farm owners. And when the farm owner also have to pay a one-time upfront cost to get the license. So here is also like a first price auction, so you pay as bid. And in Germany, in the past, they like subsidize the wind farm production, and they use like a strike price auction. Basically, ask the bidders submit a minimum price they want to have to build this wind farm, and then if you ask the lowest price, and you will win this auction, you will get the license. And in this way, all the investors will get the minimum price guarantee, because if the market price is higher than what you asked, okay, you will get the surplus. But if the market price is lower than what you asked, the strike price, and the government will make up the difference. So basically, you have some like price floor for this electricity generation. And in our study, we just focus on the scenario the wind farm investors don't need compensation for building this wind farm. So basically, we assume it's a very optimistic scenario. They will earn enough profit to cover the cost. Okay, in this scenario, we want to know that, okay, what's the best design for this auction or policy to promote the wind energy? And obviously, it's like a classical auction design problem. As we know, like last year, the Nobel Prize, Paul Milgram and Robert Wilson, and they are winning the prize because of their work in the auction design. So basically, we want to select the most cost-efficient electricity producer, and we want to induce the winning producer to build and maintain the wind farm. And here, like we consider two important policy instruments. And the first one is a price guarantee, and the second is a price subsidy. And the price guarantee basically means that, okay, if you think of the owner of the wind farm, right? And right now you have to decide how much you want to pay for the license, but you hope like receive some like revenue from the electricity market in future. But we all know like the electricity price is uncertain, right? You just forecast how much it is, and maybe it's very different from what you forecast, right? And for that, you bear a huge price risk because of this uncertainty. And for the investors will know that, okay, if they don't like risk, okay, if government can tell them, okay, I give you a fixed price of electricity in 20 or 30 years in future, and then the investors has like no risk in this perspective. And the second instrument is a subsidy. So people can ask, okay, given like the wind industry can earn positive profit to cover their cost, and why you still need the subsidy for that, right? And the answer to that is, okay, because for the government, the wind energy, the value is not only like the market value of that, right? Because if you think of like a CO2 emission target and so on, so basically promote wind energy, basically you reduce the CO2 emission of the whole country, right? And for that, like probably the government value the wind energy not only equal to the market value of the electricity, but maybe also other like a political like value and so on, right? And the shadow like value of the wind energy. For that reason, a government can like give a subsidy to the wind farm and to promote the production of wind energy. And we try to study whether these two policy instruments are effective or not to achieve the government aim. And we use the lab experiment. And now I go to the setting of our lab experiment. And first we capture the feature is like an uncertain electricity price in the future, so which implies uncertainty revenue for bidders. And the winners must invest before knowing the electricity price. If you think of the timing of this like wind farm, right? And they first get a license and then decide have to build that certain capacity. And after several years, and they can deliver the power to the market and get the revenue and so on. And the third feature is bidders face a common uncertainty about how costly it is to build the wind farm. And if you think of this, it's more like in the equipment part, for example, like wind turbines, right? And basically they have to buy from a certain like a supplier, and no matter who built this, if you buy certain like equipment, you have to pay the same cost. But for that, we also notice that when you like bid in this auction, you don't know how costly the equipment will be in 3 years, for example, right? So there's also like some uncertainty about this part. And we also assume like bidders differ in production efficiency. So basically, given the same equipment and the same location, same capacity, and the bidders can have a different capacity factor. The reason can be like they have a different operation strategy, right? They can optimize that or not, and so on. So they have a difference there. And also we assume like bidders are protected by limited liability. For example, if the price is not enough to cover the fixed investment in the future, they can go bankrupt, and then there's limited liability. Okay. So go to the model a little bit. So basically we assume there's n number of bidders in this auction, and we use the first price sealed bid auction, so just like one round. And the bidders payoff is the following. So basically for the bidder, like what you earn in future, just like the electricity price times your output, how much electricity you sell to the market. And you have some like variable cost, and the variable cost related to how much you produce, and also related to your efficiency level. So if you are very efficient, so basically produce 1 unit electricity, your cost is lower. And the last part of the payoff is the fixed investment. So basically you have to buy equipment or operate that and so on. So that's like some fixed cost. For the fixed cost part, we assume everyone like in the auction so receive a signal. So basically a signal you can interpret as like estimation about the future fixed investment cost, right? I estimate how expensive the equipment and so on. And then everyone get a signal, and the signal is not perfect in the sense that, okay, maybe there's some difference between your estimation and the realized cost. And for simplicity, we just assume the real, like the fixed cost equal to the average of every bidder's estimation. So you can think that everyone estimates something, at the end you just take the average, then the average is a realized cost. And for this cost, we assume like a very simple uniform distribution between 0 and 300, and everyone get an independent signal. And the productivity is also like the private information. So basically every bidder only knows his own productivity factor, and doesn't know other people's productivity. But we all know like the productivity is a random draw from uniform distribution between 6 and 10. So in this sense, like you can guess like what's the average of the other people and so on. And finally, the electricity price is also uncertain. So for simplicity, we just assume the uniform distribution for this electricity price. There's like a lower bound and upper bound. And for that, we can see immediately it's quite different from reality, right? Reality can be like, for example, normal distribution of this electricity price, right? And so you can see that all this distribution is very simple. It's just uniform. The reason is we implement this in the lab. So basically we try to help like the participants in our lab understand the mechanism easily, because the uniform distribution is very simple and very easy to understand. And that's the reason why we all take this uniform distribution, even though it's a little bit different from the reality. But for that, like we still can carry out our study and to check like whether some policy instrument is effective or not. Okay, for experimental design, so basically we vary 2 dimensions. And the first dimension, whether you have a price guarantee or not. Okay, in the baseline, there's no price guarantee. So basically means that all bidders face the uncertain price, such a random draw from this distribution. And the second dimension is a subsidy, whether you receive subsidy or not. So here's a subsidy, just a fixed subsidy, and is on top of the market price. And no matter what the price is, and then you will receive this subsidy. Okay, according to this two variations, we get 4 different treatments. And the baseline is no price guarantee, no subsidy. And then we have price guarantee, no subsidy, or no subsidy and price guarantee, and price guarantee plus subsidy. So for this, we can see that, okay, the price guarantee just give you a average price level equal to 50. And if you have a subsidy, here's the subsidy level is 3. So basically, no matter what the price is, you will get additional 3 units. And if you have a price guarantee and a subsidy, then overall is this 18. Okay, this experiment is between subjects. It means that, okay, for all players in this auction, you only experience one time in one of these 4 conditions. And there's a fixed group for each auction, there's 3 players. They compete for this license. And then overall, we have almost 200 students participate. And for this game, we played 25 rounds, basically offer a chance for them to learn how to play this auction. And subjects start with an endowment 12 euros. And then the final payment for each player is the maximum how much they earned. Because they have a 12 euro endowment, they earn over 5 random rounds, because they play 25 rounds and we randomly draw 5 rounds for that. And notice that in this scenario, if there's no price guarantee or no subsidy, so on, and players can earn negative profit, maybe. The reason is if they overestimate the price, right? They believe in the future the price is very high, but the realized price is very low. So they bid too much to get the license, and at the end they will get a loss. So to make sure students don't lose too much, and because they play the game for probably 1.5 hours, so we give the minimum payment for that. So basically, if you earn less than 4 euros, you will get 4 euros for sure. So this 4 euros is a minimum earning guarantee for them. Okay. So hypothesis. So based on this setup, and we first specify what's the government payoff. So as I said before, the government value 2 things in this auction. The first thing is a revenue, how much I can get to allocate the license. So this part is the B1. So it's the highest bid in the auction. So it's the government revenue. And the second part of the value from the production of electricity. The reason is I argued before, government value the wind power because it's green, right? It is help to reduce the CO2 emissions. So government want to have more. So in this, government have some kind of shadow price for this output of green electricity. And the other cost for the government is a subsidy. If you decide to give subsidy to the producer, then you have to pay the subsidy. The subsidy times the output is the cost. So overall, it's the government expected payoff in this auction. So we assume the subsidy is 3 and the shadow price is 7, and we figure out its optimal subsidy level is 3, given the shadow price of green electricity is 7. Okay, the first hypothesis is we have is price guarantee will reduce, okay, so in other way around, the government revenue is great with a subsidy than without subsidy. So basically, if you give subsidy and the producers will produce more electricity, and then given you have some shadow price for that, and the cost of electricity is the subsidy is less than the shadow price. So in this sense, if you give subsidy, you will promote more green electricity, and then your revenue for the government is higher. And the second hypothesis is government payoff is great with price guarantee than without. The reason is if you give a price guarantee, you just take away the price risk for producers and producers are more certain about the future revenue. So they probably will like bid aggressively in the auction. So this generates a higher bid revenue for the government. And another dimension, they probably will invest more and then produce more electricity. And then there's essence also good for the government. Okay, now we look at the results. And first look at the bid in this auction. So basically here is 4 different scenarios. The NSNG basically means that no subsidy, no price guarantee. And the second is no subsidy, yes, there's a guarantee, price guarantee. And the third one is no subsidy, yes subsidy and no price guarantee. The last one is you have subsidy and you have a price guarantee. And from this bar, you can see that, okay, if we consider first thing is whether the subsidy increase the bid revenue for the government or not. And you can see that, okay, compare this no subsidy, no price guarantee with this, yes, subsidy, yes, no price guarantees. For this, like only changes whether you give subsidy or not. You can see that, okay, subsidy increase a bit. And similarly, if you fix the price guarantee, and see, okay, there's no price subsidy and there's price subsidy, you can see that the price subsidy also increases the bid in this auction. So basically it means that no matter whether you use like price subsidy or price guarantee, and both can increase the bid in this auction. And obviously, if you combine this together, the increase is the most high level. Okay, the second we look at the government payoff. So basically here is overall, it's just like not only the bid revenue in this auction, also the value of the output and minus the subsidy. So in this scenario, you can see that, okay, overall, if you look at that, so the last column, right, last bar is yes, price subsidy and price guarantee. If you have this both implemented, and the government payoff is highest than other. And strangely, if you have like price subsidy and no price guarantee, and the government payoff will be the lowest. It's even worse than no subsidy, no price guarantee. And then we look at efficiency of this auction. So efficiency will mean that how efficient for this auction to select the most productive producer. So basically, we know that at the beginning in this auction, there's 3 players. They have a different efficiency level. So this is productivity level. And if this auction is good, so basically you should like select the most productive producer, right? So basically the winner should be the bidder with the highest productivity. And for that, we can look at this efficiency level. So basically here is like the percentage to select the most efficient, most productive bidder in this auction. And you can see that, okay, in the baseline, it's only about like half chance to select the most efficient producer. But if you introduce the price guarantee, and you can see that the efficiency level increase a lot, right? And similarly, if you give the subsidy and introduce the price guarantee, and the efficiency level also increase. And for this, and if you compare the no subsidy, no price guarantee with yes subsidy, no price guarantee, you will see there's no difference between them. So basically, in this perspective, only effective instrument policy is price guarantee. So basically, price guarantee can increase this like efficiency to select the most productive producer. And okay, that's going to finish. Thank you. And the last thing is the variance. So basically, government not only like care about how much the payoff is, also care about okay, what's the variance of this. And you can see that if you combine like a subsidy and the price guarantee together, the variance reduce a lot compared to the baseline. So basically, to conclude, so government payoff great with price guarantee because guarantee both the efficiency and both the bids, and the government payoff only great with subsidy in case of price guarantee. the price guarantee and the subsidy combined dampen government payoff volatility. So the suggestion is, in reality, even though there's a positive profit for wind farm industry, and the government should use the price guarantee and the subsidy to promote wind energy. Okay, that's all. Thank you.
Thank you very much. Is there some question from the audience? Again, maybe I can start just to give a little bit of time to people, for other people to also prepare their questions. I was wondering, what we saw in your analysis is that indeed we can use this type of tools to, let's say, both the subsidy and the price guarantee to somehow increase or stabilize the payoff that the government is receiving from auctioning wind power. But what is the effect of this on the development of wind power? Is there any way to acknowledge this as well? You mentioned something about selecting the most productive bidder, if I am not mistaken.
Yeah, so and here, like, please.
Yeah, I was wondering if this is significantly different, let's say, the selection of the most productive bidder between the different mechanisms. Maybe.
Yeah, so basically for that, like, this basically means that for this auction, like, okay, first, like, we think this given, like, the location, right? And given whatever, like, the weather condition, forecast, and so on, right? And the bidders just decide how much I want to bid for this license at this location. And for that, like, you select the productive producer, basically means that they reflect, because you cannot really observe their productivity, right? You can only, like, say, okay, in this scenario, like, who want to bid more, and okay, the winner is like the one who bid more, right? But given if you promise some price guarantee, and then there's no risk in the market side, okay, even though they have a different risk attitude towards the future price uncertainty, and if you take away this risk, and then it's much easier to let the most productive producer to win. The reason is, like, okay, the revenue is the same, right, for everyone, and I know I have a lower cost to produce this electricity, then I would like to bid more, right, than you, if, like, I have higher productivity than you. So in a sense, like, the price guarantee can help to select the most productive bidders. If there's no such guarantee, and then you can imagine, like, okay, I'm more productive than you, but I'm more risk averse than you, right? Then, like, in the auction, I will bid a little bit less than you, and then you are the winner, right? And there's like a kind of trade-off there, like just like a risk attitude may play a role.
Okay, maybe I have missed something in your presentation. So if you allow me just a clarification too. What about the volumetric risk? So the risk of the power output. Is this the same for all the bidders? So they have the same type of.
No, so for that, like, it's basically okay here. So if you look at the bidders payoff, so basically what we assume here is, like, for a bidder, like, if you win, right, the auction, and then you allow to build, but how much you produce is your own decision. But basically, we assume that, okay, you don't know the price level, but you have to decide how much you produce. And this, you can think of this as, like, some kind of, like, a long-term output planning, right? Like, given the license I have and how much I produce, and depending on, like, at the beginning, how much I put, like, the equipment on, and so on, and the operation strategy, and so on. So this, like, influence the future, like, output. So for that, like, the bidder's output is a decision for the bidder. Okay. It's not a given. It's not like everyone produces the same, like, output.
No, because in reality, if you look at wind power, as we were also seeing in the previous presentation, how much you end up producing is quite uncertain. So this is a major source of the risk for the bidders.
Yeah, that's true. Yeah. So for that, like, maybe, like, the difference can be, okay, something is about weather condition you cannot really control, but something you can control, we reflect that into the productivity. So basically, if you are more efficient and given the same condition, same price, you will produce more than other people. So that's in that sense why like the most productive bidder is very important for the output. Yeah.
Okay, but the productivity is revealed after the bidding, right? So this is uncertain when the
no, the productivity in our experiment like is given, like before
okay.
the auction, you know that. So everyone knows his own productivity, but you don't know other people's, and then you compete for the license.
Okay, so this means that when you're deciding, you have all the information about the future somehow, right?
Yeah. So basically, yeah, right. And the future, the only uncertainty is about the price. So then you have to decide how much you want to produce before knowing the price. And that's like where the uncertainty comes from. The other part is like a fixed cost of the equipment. It's also uncertain. Yeah.
Okay. Maybe somebody from the audience or the other presenters also want to participate in the discussion here of this interesting work. Again, please use either the chat or unmute yourself directly to ask a question. Okay, it seems that this was quite clearly presented. So let me thank you for this very nice presentation, so that we slowly move on to the final paper, three-paper session. Thank you very much. So the final paper is following on the same topic. Incidentally, it's another topic about ensuring renewable energy production by means of the auction mechanism, focusing on the situation and the mechanism in France. This will be presented by Clement Leblanc, who is a PhD candidate in economics at CEST, that Centre International de Recherche sur l'Environnement et le Développement. I'm sorry for slaughtering the French acronym. So this is an interdisciplinary research center dedicated to the study of sustainable development. The thesis of Clement focuses on a microeconomic analysis of subsidy mechanism for wind and solar power generation. Prior to starting a PhD in October 2019, he graduated from Yonsei in economics and statistics and from Agro-Paritech in environmental economics. He also worked for 3 years as an economic consultant for a consulting firm specializing in environmental issues. Before that, he had prior work experience at the OECD Environment Directorate in an economics research center at Kyushu University, Japan, and at Enerdata. I see the shared screen is already working, so please, the floor is yours.
So thank you for the introduction. So yeah, I will be presenting a case study on some wind productions that were held in France, which illustrates some pitfalls of ensuring production risk. So the general context of our paper is a kind of support mechanism for renewable energy, for solar and wind power in particular, which is feed-in tariff contracts, so that guarantee a fixed price paid for any amount of electricity produced by a renewable producer. And these contracts are more and more often awarded through auctions, meaning that the producers asking for the lowest level of subsidy will win these auctions and be selected to be eligible to these subsidies. And we regard this mechanism as contingent auctions. So what we mean by that, or what the idea of the contingent auctions is, there are auctions where the payment that is made to the winner, so here we are in a procurement setup, so payment made to the winner will depend on a future event that did not occur yet at the moment the auction takes place. So here, this event would be the amount of electricity to be produced by the power plant. And this event is exposed to this probability distribution, to an exogenous risk, which here could be either weather variability, whether you have nice weather for the production of your wind turbines, or it could also be a misestimation of the wind resource ex ante before building the power plant, and finally find out the wind production is lower than expected. So to compensate for these risks, what the literature stresses is that there are usually risk premiums that are added to the bids by bidders participating in such auctions. And so this will, in the end, increase the regulator's cost for subsidizing this power plant. And also the literature stresses that an appropriate contract design may help to limit these risk premiums, and in the end to reduce the cost for the regulator to subsidize these power plants. So the general idea being to develop renewable at lower cost. So that's exactly what the French regulator tried to do in France with 2 waves of auctions that were regarding offshore wind farms, so 6 offshore wind sites, which were subsidized through feed-in tariff contracts already through auctions. But the specificity of these auctions was that these feed-in tariffs were implemented with a modified payment rule. So what happened is that the firm participating in the auction were asked to at this stage of the auction to state to self-report what their expected yearly production is, how much they expect to produce in average, and then once they won and they build the power plant and get the subsidies, the regulator provided an insurance that in the firm that as long as their yearly production remains within a 10% interval around what they stated was their expected production at the stage of the auction, then as long as they remain in this interval, their payment vary very little. So this payment rule is represented here on the left graph. So what we call by payment rule is the payment made to the firm depending on how much she produced. So on a typical standard feed-in tariff contract, this would be simply a linear relationship, which is represented here by the dotted line. But this modified payment rule provided that as long as you remain in an interval around the expected production, so say your expected production is this vertical dashed line, then as long as you remain in the gray area around it, you can see that your payment varies very little. And the result of that is that the probability distribution of the winning firm's revenue is much more concentrated than what it would be under a standard feed-in tariff. So you move from the light blue to the dark blue with this modified payment rule. The problem with this mechanism is that the participating firm might be tempted to lie on their expected production, because by doing so, say they report an expected production that is Q0 above this vertical dashed line, then by doing so, they are most likely to benefit from the insurance mechanism, meaning to see their revenue inflated by this insurance mechanism. To put it otherwise, they will be compensated by the regulator because from the point of view of the regulator, the firm performed badly compared to what she expected, because she said that she was expected higher than its actual expected production. And naturally, the consequence of that is that it shifts its distribution revenue towards higher values. So you see that you move from this dark blue distribution towards the red distribution, which has a much higher expected value. And by doing so, you also lost the insurance feature of this payment rule. You're not insured at all. The revenue distribution is much spread again. So what we did in this paper is that we first develop a theoretical analysis of a wider concept of production ensuring payment rule. So the French case was one example of this idea, and we developed an analysis of a wider definition of this. And then we use simulation to provide some quantitative insights of what about the French offshore wind auctions. And finally, we study whether a modified, more strategic proof mechanism would be likely to bring better outcomes. So the game we model is quite simple. We have an auction game where participating firms place a bid, except that contrary to most auctions, the bid is composed of two components. One is the price they're requiring, so the subsidy level they're asking for, and the other one is the reference production they state. So what they state is will be their expected production. And then after each participating firm places the bid, the regulator selects the lowest price bid, so based only on price. And later, the actual production is known, so that would mean when the power plant is built and start producing, and yearly production is known, and the winning firm get paid depending on price and a payment rule, so we denote R, which depends on both the actual production and the reference production that was stated in the auction stage. Regarding what reference production is stated, we have two possibilities. Either the bidder is truthful, meaning it will report the actual average expected production, its actual expected production as Q0 as reference production, or it can be a strategic bidder, meaning it will report the Q0 that maximizes its payoff for a given price. Regarding price, we made some quite simple hypothesis. We assume that all participating firms are truly symmetric in both cost and risk aversion, and we also assume cost is deterministic. And considering this full symmetry, we have price bids are determined by zero profit conditions, and we have one exception to that, is that when we introduce some heterogeneity regarding how bidders report their reference production. So if we have some bidders being truthful and some others being strategic, then we have asymmetry among these bidders, and the zero profit conditions doesn't apply anymore. To summarize what we get from the theoretical analysis, so we derive some analytical results for the broader definition of production ensuring payment rule, and we find that under very limited conditions, strategic bidders are always incentivized by such rule to overstate their expected production. We also find that such payments will in general result in lower prices than under a linear contract, linear payment rule, so standard fee tariff contract, for instance. But this can cover different realities, like if bidders are truthful, meaning they report their true expected production, then these lower prices are simply due to lower risk premiums, so that's probably what the regulator expected in the first place. But if bidders are strategic, this is simply a deceptive effect because lower prices are due to the expected revenue of the firm being artificially inflated by the insurance mechanism. So for a same price, they will get higher revenues because they are strategic. They strategically reported their expected production. And finally, we also find that when there is asymmetry regarding strategic behavior, some being strategic and some others being truthful, then the strategic firm that wins the auction is allowed to capture positive rent at the expense of the regulator. Then this will also increase the cost for the regulator. Then beyond these theoretical results, we move on to some simulation to put some figures on these theoretical results. In the specific context of the French wind auction. So the objective is to estimate the French regulators' losses magnitude. So in order to do that, we simulate firms-based response in these auctions. So in the 6 auctions that took place for 6 offshore wind farm sites in 2011, 2013. So we consider feed-in tariff contracts following the rule that was actually used by the French regulator. We consider a duration of 20 years, which is the actual one, an interest rate, which is taken from the literature corresponding to the weighted average cost of capital for such projects. We consider that firms are risk averse. We consider a utility function which is constant with constant relative variation depending on parameter gamma. And we use a proxy for the risk distribution these firms are facing. And this proxy distribution includes one component which is weather risks and another component which is the misestimation risk. So weather risk is approached using simulation based on historical weather data. So these are the outputs from the Renewable Nature website. And to obtain a large distribution of what could be one weather year, we recombine the historical years available at the quarter level. So we build many synthetic years using quarters from different years. And regarding the misestimation risk, we simply add normal noise to the firm's production, which will repeat over the 20 years, and we take mean absolute error of 5%, which is in line with what was common estimation mistakes until recently. And the results we get from that is that, so considering the standard risk aversion, so gamma equal 1, we find equal 1. We find that the risk premium under a linear contract, so under a standard feed-in tariff contract, would be about 0.3% of the total cost of the power plant. And we find that the French rule allows to divide that risk premium by 2. So we get half that risk premium, provided that bidders report truthfully their expected production. But if bidders are all strategic and competing, being strategic in the auction, then these gains are simply lost. But we have a worse situation where there is one strategic bidder and the others are truthful bidders. And in such case, the strategic bidder is able to capture a rent that would be 15 times larger than what we hoped would have been gained in the best case where all bidders are truthful. So that was for very standard risk aversion level, and you see here that when we vary the risk aversion level, you need to go very high, have totally unrealistic high risk aversion level to find situations in which the cost for the buyer would be lower, even in the presence of strategic firm. So that's not totally impossible, but that's possible in total unrealistic risk aversion level. Finally, we consider whether we could improve this payment rule by making it a more strategy proof, sort of. So the idea would be was to discourage a firm to lie on their expected production, and what we considered for that was to add punishment to payment rule that ensures. So we have a plateau in the middle. So as long as you're around the expected production you stated, you're fully insured. You get the same payment all the time. But if you fall out of this plateau, then you get more or less severely punished, meaning you get lower revenue, so rapidly decreasing revenue if you fall below, and no additional revenue if you're above, or limited additional revenue if you're above it. And so we have a whole set of possible payment rules depending on these two parameters, so the width of the insurance and the harshness of the punishments. And we simulate the firm's best response when facing such payment rules and production risk, which is a normal distribution with a standard deviation equal to 20% of its mean. So what we get from this simulation is these graphs. So on these graphs, on each of these squares, what you have is the space of possible payment rules on payment rules that have been tested. So when you go towards the right, you have a larger insurance, and when you go upwards, what you have harsher punishments. And if you're in the bottom left corner, it is actually the linear contract, no insurance and no punishments. So a standard feed-in tariff contract. All these three first graphs represent the cost for the buyer resulting from the auction. So if you take, for instance, the first graph where representing the situation where all firms bid truthfully, what you see is that when you get a wider insurance, you move to lighter colors. So that means a lower cost for the buyer, a lower cost for the regulator. But when you move upwards, meaning harsher punishments, you move towards higher cost for the buyer. So this is simply due to risk premiums. The more the insurance, the larger the risk premium, the lower the risk premiums, and the more punished, the higher the risk premiums. So all these three are payment made by the regulator. And the last graph is the expected production that is reported by a strategic firm in such auctions. So areas that are blue, in this part of the graphs represent overstated expected production, and brown represent understated expected production. And what you can see here is that you have a white line representing a set of strategic proof mechanisms. So you have a good equilibrium between insurance and punishments, which discourage even strategic firms from lying on their expected production. And when you move to what is the cost for the buyer when you have strategic firms, so that's graph 2 and 3, you see that these strategic proof mechanisms perform kind of better than the average. The cost doesn't increase as fast as in other areas of the graph, but actually you can also see that the best performing mechanism is still the linear contract. So even none of these strategic proof mechanisms perform better than the standard feed-in tariff contract. So to summarize, this family of payment rule doesn't bring a better outcome under a normal distribution. So just to summarize quickly, we showed that such production ensuring payment rule implies strategic behavior by self-reporting an overstated expected production. So due to that, it failed to reduce the risk faced by firms, and it may even increase the cost for the buyer due to either an increased risk for the winning firm or rents that are captured by the strategic firm facing truthful firms. And just some final remarks to conclude. So one may think, saying that the simple solution would be to control for the reported expected production. So for instance, have a third party certifying the capacity factors that are reported by the firms. So that is actually the tool that have been used in some countries for similar mechanisms, but this actually opens the door to other problems, such as, for instance, manipulation or corruption of the third party. You might be willing to pay or to put some effort in order to make the third party think you have a higher expected production than he thinks. You might have effects such as inefficient selection, so the firm that has been lucky in the determination of their expected productions, so meaning their expected production have been overstated, are more likely to be selected than other firms and might be inefficiently selected in the process. And also you can imagine that there would be a kind of moral hazard equivalent to the issue that have been presented here, meaning that once the auction took place and the firm wins, you may expect that the firm will have an incentive to downgrade or not make as much effort to maintain its expected production, knowing that it will be paid almost as much by not doing so. And I don't thank you for your attention, and I'd be happy to answer any questions.
Thank you. This was a very interesting presentation. I see Nicolas has already raised his hand, so if you wish, you can unmute yourself and open your camera to ask your question.
Thanks a lot. Hi, Clement, nice presentation. Just a question, because in other contexts, the same regulator has used tool based on the ex-post internal rate of return. Like you can let the product live, look how much return on investment they get, and use this ex-post measure as a way to have some insurance ex-post mechanism. So I was wondering whether you also try to use this as a measure for ex-post insurance instead of production. And if you did, like, do you have any idea of why they've been using production in this case and they use the IAR in those settings?
I'm sorry, I'm not sure I couldn't understand.
I mean, for other renewable product or for interconnectors sharing mechanism, sometimes what the very same regulator does is, like, they look at the cash flow ex post, so they look at what happened, and so you can compute the return on investment for this product, what's the internal rate of return of this thing. And you can base your insurance mechanism for the investor based on directly on how much money they made on their capital investment instead of what production level they achieved.
So you're thinking on rate of return regulation, so some such mechanism.
Yeah, it would be more in the kind of La Fontiero kind of
okay.
spirit, although it's the measure, the tool you use is slightly different, but or more generally, like, have you considered other parameter you can fine tune to kind of build in insurance in the mechanism, or is it just production? And if so, I guess my question is why focus insurance on the production level instead of any other way you could have to provide insurance ex post?
Okay, so so you're thinking like you could base insurance on the cost of the firm instead of having the
revenue. I mean, you could say
but
here revenue is lower than X person, then we provide you some extra cash exposed because
okay, but then here we are in a setup where feed-in tariffs provide the whole revenue of the firm, and it's entirely based on production. So there is no other variability of the firm's revenue than its production. So that
no, but using production kind of force you into one-dimensional tool in how you can provide insurance, but you could have like lump sum payment, which would just be like if you it kind of force you to have a payment that is proportional to the amount of production, but you could have an insurance payment that is fixed or that is
maybe I can also offer my own explanation to this, even though I'm not an expert. Let's say possible answer to this question is the fact that production is naturally uncertain. So basically, the justification for providing the insurance is indeed the fact that even the best forecasting system, let's say, would fail to do so. If we go to the revenue, this is not exactly naturally uncertain because it's subject to all the decisions of the firm. So the mechanism, I think, is clearly targeted to protect against this uncertainty that there's no way of living without it, if you wish. But that's just my assumption.
Yeah. Yeah, so actually, of course, there is an uncertainty to the amount of production that such power plant will produce. But I'm still not sure what. I understood what kind of mechanism you, Nicola, had in mind, but actually you can see this such mechanism kind of as an intermediate between what would be a fixed price regulation, whether against a cost plus regulation. So you have something like your payment, the payment you receive depend on your production, but not too much, and I don't know, like a lump sum payment is what you would suggest.
If you take a graph on so here basically your insurance is like you kind of create a flat region in the middle.
Yeah.
You could have some kind of different insurance, which would be you kind of flatten the tail and leave the slope in the middle. I mean, you could have like.
Okay. But then, actually, the idea of flattening the term totally enters the tail. So as long as it's symmetric, so as long as it preserves the main revenue of the firm, any flattening of the payment rule anywhere would totally enter what we considered as production ensuring payment rules. So the simulation we made it don't cover it, but the theoretical results we have cover any payment rule where you have which induce the same expected revenue, but a lower variability of the revenue. So if you have a linear payment in the middle and flat on the sides, that would enter the production ensuring payment rule definition we used for the theoretical analysis.
Okay, and you still have this bias incentive.
Yeah. Yeah.
Okay, I think this was a very interesting discussion. I don't know if we have time for one more question. If somebody wishes to ask something, either to Clement or to the other speakers that are still here with us. Okay, it looks like we will finish shortly before the scheduled time. Thank you very much for these very nice presentations and to the audience for the participation.
Thank you.
Okay. Thank you. Thank you very much.
Yeah.
Nicola, you want to add something or okay? No, it's just me. I saw the raised hand. All right. Let's just finish. Sorry about that.
Thank you, dear speakers. Just a quick message from the organization team. Can you please upload your presentation in your dashboard? Thank you very much.
Thanks.